Hi there, so this is the Avondale College practice exam for probability distributions 2017, and we're going to do question 1A in this video. So here's question 1A. Now a good idea with a question that has heaps of words in it is to actually start by reading the goal or the instruction first, and then you kind of know where you're headed. The instruction is to sketch the graph of an appropriate probability distribution model for flight time. So that's what this first part of this question is actually about, sketching a distribution. So we should be thinking, I wonder what sort of distribution model is going to be the best one here. Now as we start reading the information, we know that's where we're headed. Okay, so an airline has 2 flights from Dunedin to Auckland. The airline claims that flight A will take 1 hour and 50 minutes. But in reality, the flight could take anywhere from 1 hour 45 minutes to 2 hours and 5 minutes, with all times in between being equally likely. Okay, so already we should be thinking, okay, what sort of distribution would that be? All times between being equally likely. Well, there's only one distribution model that caters for that, and that is the uniform distribution, or rectangular distribution. Okay, so we know we're going to be drawing a rectangle. The airline claims that flight B will take 1 hour 45 minutes, but in reality it could take anywhere from 1 hour and 35 minutes through to 2 hours, with all times in between, again, being equally likely. Okay, so using an appropriate probability distribution model, sketch each distribution on the same axes below. Okay, so we're going to need a scale here, and obviously when you're using hours and minutes that gets a bit tricky. So what would be an easier way to express the time scale for this, do you think? I'm going to go for minutes, so I'm going to convert all of these times into minutes, and that's the first thing I'm going to do, is write alongside them what they are in minutes. So 1 hour 50 minutes, that is how many minutes? 110. And I'm going to do that with all the times. And that's a good idea. Write it over the top so that you can actually see what numbers you're going to need to be showing on the graph. So why don't you pause the video and do the same. Okay, cool. So now we can see we need the scale to go from what? From 95 up to at least 125. And so I can count the number of columns I've got to work with and work out the easiest way to do that. There's a few ways you could do it. I opted to start at 95 and make every 2 columns count as 5. And labeling it flight time in minutes. Okay, next thing we need to work out is the vertical scale. So when you're dealing with a probability distribution, is the vertical scale probability? Have a think about how do we represent probability when we're dealing with a continuous variable like time. We can take any value to any number of decimal places. Well, we use areas, so that the total area under a distribution for continuous data should equal 1. So therefore the height is really just a means of working out the area. And if you think about it with a rectangular distribution or uniform distribution, the area of a rectangle is what? Base times height. So the probability is going to be the base times the height. So the height, some people call it the function's value, or f of x. Really all you need to think of it is it's a way of working out the probability. It's what we need to multiply the base by in order to get the area, or the probability. So I need to work out the height so I can number the scale, and that's important because that's going to give me an idea of the proportions involved. So how do we do that? Well, we know the area is base times height, and if we start with flight A, because flight A is going to have its own distribution, as is flight B. Flight A has a base of what? So flight A's flight time is ranged from 105 minutes through to 125 minutes. So that's a range of 20 minutes, isn't it? So we have height equals area divided by base, because base times height equals area. So what's the area of any probability distribution model? Well, it has to be 1, because the probabilities of any distribution have to add to 1, don't they? So area is 1. Base we've worked out is 20. So the height is 1/20th, or 0.05. And we don't have any units for that. We don't need to worry about them, that is. But we do need to draw it. So we've got 0.05 as the height. Now we need to do the same thing for flight B. So what's flight B's range? Its range, well, it goes from 95 to 120. So that's 25 minutes, isn't it? And so its height is going to be area divided by base again. So that's going to be 1 divided by 25. Or 0.04. So our vertical axis has to cover a height of 0.04 for flight B and a height of 0.05 for flight A. So if we number it like so, going up in 0.01s, then we can plot them. Firstly, flight A, which goes from 105 to 125 and has a height of 0.05. So here's flight A, and now we need to plot flight B. So flight B goes from 95 minutes up to, let's have a look at the question again, up to 120 minutes, and it has a height of 0.04, like so. So really important to get the credit here, you had to have, or to get full credit, you had to take into account the height as well as the base, because of course that's going to affect the area, and the area is what represents the probability. Okay, so use your model to calculate the probability that flight A and flight B will both take longer than the airline claims. So, starting with flight A, the probability that flight A takes longer than claimed, they claim that flight A will take 110 minutes. So, longer than 110 means from 110 up to its maximum, which is 125. So, that's a base of what? Base from 110 to 125, there's a base of 15 minutes. So, 15. And the height for flight A is 0.05. So that's going to be 15 times 0.05. So what does that equal? 0.75. So 75% chance that it's going to take longer than claimed for flight A. It's not ideal, is it? Okay, for flight B, their claim is 105 minutes. So if we look at 105, what's the area to the right of 105 for flight B? Let's have a look. So it goes from 105 up to 120, so that's a base of 15. Again, but for flight B, the height is only 0.04. So it's going to be 15 times 0.04. What's that? Well, we know that 15 fours are 60, so it's going to be 0.6. So there's a 0.75 probability that flight A takes longer than it claims, and a 0.6 probability that flight B does. So the probability that they both do, well, if those two flight times for the two airlines are independent, then we can estimate the probability of both by multiplying those separate probabilities. A bit like if you flip a coin twice, its probability that you'll get tails twice you find by multiplying 0.5 times 0.5 to get 0.25. So it's the same sort of thing. So if independent, we can multiply them. So probability that both take longer than claimed equals 0.75 times 0.6. And that equals 0.45, which is our answer. Now, it says give any assumptions. Always look for that because you otherwise miss out on the full credit. So the assumption is what? The assumption is of independence. Specifically, we're assuming that the flight times for flight A are independent of the flight times for flight B. Because when you multiply two probabilities to get the probability of them both happening, that assumes that the probability of the first event has no influence on the probability of the second event. Like tossing two coins. Okay, so checking our answer. Yeah, we've found the probability the question's asking for. That's what we were asked to do. Using the model, which is a uniform distribution model. And then we've also talked about the assumption of independence. So if we go to the marking scheme now and have a look, and we can see that it says for achievement, one rectangle drawn correctly including correct height, or two rectangles drawn without heights identified, but rectangle B is shorter than the height of rectangle A. Should be 1/5 shorter, but we were a wee bit tolerant with that. It achieved. And then for part 2, correct probabilities calculated for individual flights, so 0.75 and 0.6. For merit, which was the maximum, you had to have both rectangles drawn correctly, including correct heights. Okay, because without those you can't compare the areas. And also correct joint probability. Joint probability is a fancy term for just the chance of both things happening. So that had to be calculated, and the assumption given in context. And their assumption, they said, was assuming that both flights' arrival times are independent of each other. And it says, no, must identify that it is the arrival times of the flights that are independent. Okay, so to practice another question like this, go to question 1 of the 2016 probability distributions exam, which you can get from the NZQA website. And that is a really similar question, so that you can apply your newly found knowledge and skills to that. All the best. See ya.